Hello everyone, this is Dr. Young, and in this video I'm going to talk about dilutions. So we're still talking about aqueous solutions. You have the concentration of some solution, but oftentimes we may want to dilute it for just a variety of reasons. So first, let's talk about dilutions you might have seen in everyday life, right? This is not an uncommon thing. Oftentimes we buy something as a concentrate and then we dilute it to get the concentration that we want. That's all a dilution is you're more or less, especially for our cases here in Gen Chem, and in your case, like in your day-to-day lives, probably you're diluting things with water. And again, it's just to go from something more concentrated to less concentrated. And in fact, let me just put that on this example here, right? We have orange juice, right? Concentrated orange juice that you might buy in the freezer section. And you take it home, you just have this little can, and then you add a bunch of water to it so you get a whole pitcher of orange juice. So we'd go from the more concentrated, so concentrated, which is what it flat out says on the container somewhere, fresh, frozen, concentrated, to the more dilute juice, the juice that is a little more palatable, it's not quite so strong. And in this case, it has instructions, right? It says keep 1 can, so 1 can of concentrate. And the instructions say to add 3 cans of cold water. Is going to give you, right, basically 4 cans worth, however much that is. Apparently each can is 12 ounces, but we don't have to get into that. 12 cans worth of orange juice, right, of not concentrated orange juice. Now, in this case, we have a 1 to 3 dilution, right, because we had 1 part of the concentrate to 3 parts of the thing you're diluting with. So this would be a 1 to 3 dilution. And that terminology is used sometimes, certainly a lot in household products. Sometimes in chemistry too, you might say, I have a 1 to 10 dilution or 1 to 5 dilution or something like that. This would be a 3-fold or 5-fold or 6-fold dilution, right, to make our orange juice. So orange juice is one example of a sort of everyday example. So here's another example of a sort of household product. We have Simple Green, which is just a cleaner. And on the back of the concentrates, you can buy it as a concentrate, it has instructions on how to dilute it, right? So here's dilution, dilution, dilution. So if you want really heavy duty, you just mix 1 to 1, right? 1 part of this concentrate to 1 part water. That's a 1 to 1 dilution. General purposes, 1 part concentrate to 10 parts of water. Now this example is not quite right. I think there's like 8 ounces in a cup of water, so that's more like 1 to 8, but still, it's about. Or light cleaning 1 to 30, right? So here's different ways that you can make the concentration of your cleaner fit the purpose that you need it to satisfy, right? Whether you're doing light cleaning or heavy duty cleaning. And I just want to point out, we've been talking a lot about concentrations. Here's another concentration that I saw on this molecule, right? This VOC stands for volatile organic compounds, and it's saying it has less than 5 grams per liter in this solution. So it's considered to be as a low VOC product. So 5, I believe it's low VOC. Certainly diluted is a low VOC. Regardless, here's a concentration, right? 5 grams per liter, 2 units. It involves a liquid. It's a concentration. So how would I calculate, right? If I found out that the main product in this, or the main cleaning ingredient, was like some ethoxyethanol or something like that, how would I calculate the concentration going from the more concentrated stuff to the more dilute stuff? So here's kind of just a real generic example, then we'll get into some specific ones. But like, let's say, right, that you have in here, right, you have 100 milliliters, so here's your 100 milliliters, and you have 0.50 moles of this CH3O, this methanol, right? That would mean your concentration is 5.0 molar, right? That's the concentration of this solution. Now, if I take that solution and I add to it, add another 100 milliliters, or 100.0 milliliters, right? The idea is that I've now, and you probably know this, right? I diluted it by a factor of 2. So I would now expect it to be half as concentrated, right? Before I even like draw anything out here, right? So, well, let me just do this. I fill it up to 200, but it still has the same 0.50 moles of the methanol in it, right? Because I didn't take any out, I didn't add any. I just added water. Let me be more specific here. I just added this many milliliters of water. let's do this. Let me erase this entirely. I just want to be super clear. So add 100.0 milliliters of straight up water, right? So we've doubled the volume, or in other words, the concentration is now half, right? Because we doubled the volume, the concentration was cut in half. And if you've done any dilutions at all, that might feel kind of intuitive. If it doesn't feel intuitive, that's totally fine. What we're going to do is show you how we can actually use math to figure out these numbers exactly. I'm going to give you a little preview now, and then I'll show you more on the next page. But the idea of what you can do is you can just take their original concentration, so your original concentration, you multiply that by the original volume, where my little i's, my little subscript i's there are supposed to stand for initial. And then that's going to equal the concentration of your final stuff times the volume of your final stuff. So you're more concentrated to your more dilute. So this would be of your concentrated stuff to your dilute stuff. And all we have to do is fill in the values there, right? So my concentration, I figured out, was already 5.0 molar. And if you don't remember how we figured that out, just you'll want to go back to that previous video. There's 100.0 milliliters of that. And that equals, sorry, I shouldn't have put an arrow here. This is equals, there's an equation here, equals the concentration of the end stuff, the final concentration, but I don't know that, so that's still a variable, times the volume of the end stuff, and the volume of the end stuff was 200.0 milliliters. And then you just solve that algebraically, right? So I'm going to divide each side by 200 milliliters so that I get the CF by itself. And sure enough, you'd see that it equals 2.5 molar. That's what this CF would equal. So all we have to do is basic algebra for this. Nothing too crazy. Now you can see this equation in a bunch of different ways. I did CIVI equals CFVF on that previous slide. But you'll also see it with ones and twos, right? So C here stands for concentration. I didn't say that on the previous slide, sorry. C stands for concentration. V just stands for the volume. And your volume is going to be in like liters or milliliters. Your concentration can be anything. It can be in ppms. It can be with some percent by mass. It can be in molarity. It doesn't matter what the concentration is that you use for this equation. It still works. It's just a ratio. Now, because we're chemists, we don't use a lot of like percent by volume and stuff necessarily. We like to use molarity a lot. So you might see this written with an M instead, which is just molarity. So you just put the molarity in, and again, volume's just, milliliters or liters or something like that. It doesn't matter what the concentration is again. It could be molarity, it could be something else. The point is that you have this relationship of your concentration of your beginning thing and the volume of the beginning thing is going to equal the concentration of the end thing and the volume of the end thing. And that's just because they're related by moles, right? So what you're doing is you're getting an amount to an amount. You're saying that the beginning amount of a solute equals the same amount of the solute at the end. You don't change it just by diluting something. And again, like I keep down here, here's the I's and F's again. It doesn't really matter what version of this you see or use, as long as you have the, in my mind, I don't know why, but I tend to do the concentrated thing first. It doesn't really matter at all which side is which, but I tend to do it this way. So I'm going to do that in all of my examples, and you can choose whether or not you want to do it like me. As long as you have it arranged in your mind that you're talking about the right things, then you're going to be okay. So like, let's look at this example. You dilute 5.0 milliliters of a 3.2 molar solution to 100 milliliters. What is the molarity of the new diluted solution? So you're going to start with the thing that you begin with, your initial thing or the thing you know, which in my case is 5 milliliters of a 3.2 molar solution. The thing I'm ending up with on the other side is 100 milliliters, but I don't know what the molarity is. I'm trying to figure out the molarity. So that means I'm going to set up these right here. So 3.2 molar is the concentration of my beginning. Well, let me back up. Let's do this. I'll do this version. M1V1 equals M2V2. So molarity of the beginning thing, 3.2 molar. Volume of the beginning thing, 5.0 milliliters. And I know that's going to equal, right, the molarity of my ending thing, which I don't know, but I do know that I want the ending volume to be 100 milliliters. And then I just need to isolate my M2. So I do that by, again, just doing basic algebra. I'm going to divide each side by 100 milliliters. And I should keep my sig figs. So now you'll notice that my units cancel, right? Milliliters cancel with milliliters. I'm left with big M. And if I do that math, I find that, and let me write this out, that M2 is going to equal 0.16 molar, right? If I do this math, that's what I would get. So can you just do an algebra? You're just solving for M2. So apparently the concentration, right, if I dilute this by a factor of 20 is going to be 0.16 molar. Let's look at some more examples. And this is the only equation that you're going to use over and over and over again, right? I know I'm going to use my M1 V1 equals M2 V2. Again, what version of this equation you use is irrelevant. So I'm going to say, okay, so now the question is, if you need 250 milliliters of a 2.50 solution of hydrogen chloride, of hydrochloric acid, how much of a 10.2 molar solution of HCl do you need to dilute? So the more concentrated thing, the thing which I, again, like to put on the left-hand side for no real reason, it doesn't matter. So it's saying how much of this solution. So I know the molarity of the beginning thing, of the more concentrated thing, but I don't know the volume of the beginning thing, right? What's the volume of the solution I need? But I do know that I want it to end up as, right, the more dilute thing, I know that I want it to end up as a 2.50 molar solution, and that I need 250 mils of it. And then again, you just do your algebra. So I'm going to divide each side here by 10.2 molar, which is going to give me that V1 equals 61.3 milliliters. That's my product. So apparently I need to take 61.3 milliliters of that 10.2 molar solution, that more concentrated solution, and I'm going to dump it in something, and I'm going to dilute it down to 250. I'm going to dilute it up to 250 milliliters so that I get a 2.5 molar solution. That's what that number is telling me. Here's another way to phrase these questions. Again, they're all the same. So M1 V1 equals M2 V2. If you place 10.9 milliliters of a 0.0874 molar solution of copper 1 nitrate into a 100 milliliter volumetric flask and fill it to the line, what is the concentration of your new solution? So if you've not seen a 100 milliliter volumetric flask, here is one. And the idea is that they're used for making like really precise volumes of solutions, right? In other words, in this case, there's 100 milliliters. There's also 250 milliliters, there's liters, there's 10 milliliters, there's 2 milliliters, like these come in all different sizes. And the line we're talking about is this line. So right, when it says fill it up to the line, this is the line they're talking about. This is the line that when you get your solution down to the bottom of the meniscus, when it hits that line, boom, you've got 100.0 milliliters. That's the idea. Then you're all nice and concentrated. So it's saying that basically we're diluting something to get 100 milliliters. So I'm going to find my more concentrated thing first because I just like to start there. So my more concentrated stuff is this. I've got a little bit of this stuff. So I've got 874 molar, and apparently 10.9 milliliters of it. And I'm going to dilute it down to 100 milliliters, but I don't know what the molarity of that is going to be. So I'm looking for my M2. The volume that it's going to become when it's dilute is going to be 100, right? So I'm going from the little volume to the big volume. And I just solve for M2. So in this case, again, I'm dividing by 100 milliliters. Right, so that things cancel out, those cancel, milliliters cancel, I'm left with molar. And that ends up telling me that my M2 here, my molarity, once I dilute it, is going to be 9.34 times 10 to the negative 4. So apparently it's going to, molar, right? Because you're left with molar. So that'll be the molarity once I've diluted it. So it gets smaller, which makes sense, right? You also want to be thinking back on these questions, right? You just want to make sure that they make sense. Sorry, actually, this is to the negative 3, not the negative 4. There we go. So at this point, I want you all to take a crack at these two. It's a good place to pause. Surprise, surprise, you're going to use some variation of M1 V1 equals M2 V2, but take a minute, see if you can translate these word problems or these processes into this mathematical problem. So go ahead and give it a crack. Okay, so if you're going to go over this, your fellow chemist mixed 8.5 milliliters of a 0.911 molar solution of glucose with 112.5 milliliters of water. What's the final concentration? So here's another dilution problem, right? I'm hearing that you're adding water, that you're changing concentration, so I know it's a dilution problem. So the more concentrated stuff is this. So I've got 0.911 molar and apparently 8.5 milliliters of that stuff. And then I'm looking for, right, what's the final concentration? I'm looking for this final concentration. And the volume, this one's only slightly triggered because you have to figure out the volume, right? You started with 8.5, and they said you added 112.5. So that would just be 0, 1, 1, so 121.0 milliliters. 121.0 milliliters is the final volume, right? Because if you take 8.5 and you add, right, you mix it with 112.5 milliliters, you get 121. And then I'm solving for M2 again, that final volume. So, or that final molarity, excuse me. So I divide both sides again. Mills cancel, those cancel. I'm solving for that final molarity, which is in this case 0.063995. And there's a bunch of numbers here. But remember to do your sig fig rules. I haven't been doing them for these, but this is only two. I can only use two significant figures because of the 8.5. So this would really just go to 0.064 molar as my final volume. And you don't have to put M2 there. I just put it to emphasize it for my equation. You just say that the final volume is 0.064 molar. And for the same last one, right, you need 100 milliliters, yada, yada, yada. So same equation. You need 100 milliliters of that solution. You have this solution. How are you going to make it? So it's saying, how am I going to make this solution, right? So I know the solution I want to end up with is 0.1000 molar, and I know that I need 100 milliliters of it. I need 100 milliliters of it. I know that my starting solution is 2.50 molar, but I am asking myself, well, what volume of this do I need in order to make up this solution, right? So I need to know how much of that starting, that more concentrated stuff do I need in order to dilute it out and get that 0.1 molar solution. So I just do the algebra again. So those suckers cancel, molarities canceled. I'm going to get an answer in milliliters, which makes sense considering that's asking about a volume. And so my V1 here is going to end up being 4 milliliters. So if I was to answer this question, right, if I was to write an answer to this question, this sounds kind of like a tell me how to make it. I would say that I would mix 4 milliliters of the 2.50 milliliter solution with basically 96 milliliters of water. That's what I would do, right? Because if you mix 4 plus 96, that gets you the 100 that you're looking for, but then you've diluted it, right? That's going to allow you to dilute it. So you just mix 4 milliliters of the 2.50, sorry, not milliliter solution, molar solution, with 96 milliliters of water. And that's how you do that. So that's how you do dilutions. They're straightforward once you, I mean, the math is not hard. I think the hard part is getting these word problems into the equation. And then once they're in the equation, it's basic algebra. So practice up, happy studying, and good luck.